Welcome to the MOOC NPTEL course on Bioengineering, an interface with biology and medicine. In our effort to have some clinician's perspective for biology for engineers, today we have invited Dr. Kunal Sehgal. Dr. Sehgal is director of Sehgal Path Lab. He is MD Pathology from Postgraduate Institute of Medical Education and Research, Chandigarh, India in 2007. He finished his MBBS from State GS Medical College and KM Hospital, Parel in Mumbai in 2003. Dr. Sehgal was awarded Kataria Gold Medal for the best overall student of PGIE MER 2008. The award was presented by the Prime Minister of India in 2009. He was also awarded Silver Medal in recognition of merit during the period of his studies for MD Pathology at PGI MER. He was awarded the International Union Against Cancer International Cancer Technology Transfer Fellowship at Johns Hopkins Hospital in Baltimore, USA. Dr. Kunal Sehgal has published over 50 papers in national and international peer-reviewed journals. His research interests include flow cytometry, instrument setup and standardization, flow cytometry based minimal residual disease detection in ALL, high sensitivity PNH assay using FLAIR, research parameters on CBS analyzers. It is our great pleasure to have Dr. Sehgal with us, who is going to share you his clinical perspective and several examples where he is going to illustrate you how engineering discipline is so crucial for medicine and why clinicians still depend so much on various engineering devices, the data analysis tools, and there is so much still gaps and unmet needs which has to be fulfilled for the clinics. So, let us welcome Dr. Sehgal for his lecture.
At the outset, it's a pleasure to come here. It's my first time talking to engineering students like you, and I'd like to thank Dr. Sanjeeva for having me here today. Titled the talk, Pathology Meets Engineering or Bridging the Gap. And the idea or where it all began was, when an engineer is working, say in a lab or in a research setup, trying to build something, the ultimate aim is you want it to be used. You want that product, you want the technology output to be used massively by clients, and if you're in the medical field, by doctors and by patients. And when a doctor is looking at a technology product, he is more interested at what is the output of the technology product. And he says, well, how can I use this product for my patients? So the interface which typically an engineer looks at is the interface between the machine and the output to how the output was generated. And a doctor is typically looking at the interface from the output to the result. So I'll just show you an example of how this works. For example, if you see, this is a CBC machine, okay? This is the technology. And this is the output, which is a strip coming out from a CBC machine, which tells you your hemoglobin, WBC and platelet count. And the engineer wants to know how is the output generated, how can I better it, what was used to generate this output. And I as a doctor typically want to know what is the interpretation of this output, how can I use it for the patient. Okay. Majority of us laboratorians don't care or don't understand, and that's why we don't care, to how the instrument works or what the output is, what went wrong, and we call the service engineer, please do the needful. I want my reports today before the lab, the patient has to collect the report. So this is a typical attitude which majority laboratorians always have, and it's not out of lack of interest, lack of time and lack of understanding. And the idea is, can we bridge this gap between the engineers and doctors? And why am I talking about bridging? Because this is how I am here today possibly is, I was at my previous place of work, which is Hinduja Hospital, and I was there for 5 years. And while I was at Hinduja Hospital, we interacted casually with a few IIT faculty. And then we came to know that there is a health consortium in IIT Bombay, and Hinduja Hospital joined that health consortium. The objectives of me and Dr. Deshpande, who were heading the hospital team at that time, was can we partner with the engineers and bridge the gap between the medicos and the engineers? Can we look at indigenization of products for better and cheaper availability? And can we look at innovation in context of local needs? Because there is innovation, but you need to use it for the Indian needs and the Indian patient's purpose. So this is where we had multiple meetings, we interacted, IIT faculty presented certain papers. Then at one of the meetings, what we did is, we circulated to all the doctors in our hospital, there are 100 of them, and we said, just give us a wish list where you would want somebody from IIT Bombay to work on, which will help you improve your patient diagnosis. And Dr. Sanjeeva asked me to share a few examples from that presentation. I'm sharing that today, just to give an idea of what, how different can be a need of a doctor. And if you know the need of a doctor, you would love to work in that area potentially. And that's why I am here today. So, Dr. Balakrishnan, who is a rheumatologist, a doctor who looks at joint problems, autoimmune problems, he sees these patients very often, Sjogren's syndrome. Basically a disease where you have dryness of mouth and dryness of eyes. Now, if I asked you, do you have dryness of eyes? Maybe 5 of you will tell me. But how do I compare the dryness of eyes of patient A to patient B to patient C? There is no objective way of measuring it. Dryness of the mouth. Can you study the deficiency of saliva? Can the humidity analysis be done? Can the chemical analysis be done? There is no test available today. And I remember somebody after the meeting, one of the IIT faculties raised, can we use a bubble gum or a chewing gum and give it some color reaction, intensity of color change? And there was an idea right there. So, it was just talking and just producing an idea. So, the idea was just to share our wish list, put this wish list on a common forum. There might be somebody from one amongst you who would say, okay, this is an area which I would like to work. Another example from an anesthetist. If somebody has seen an MRI machine or gone under that, it's extremely claustrophobic, extremely loud. You're lying down with eyes closed in a sphere, in a dome. You can't see anything. You're hearing loud sounds. Can there be a silencer for the MRI machine? Okay. So why are we not building towards that? How does it help? Can we have wireless ECG monitors? In movies you would have seen ECG monitors, multiple wires to your chest, hand and legs. Why can't in today's day and age we have wireless monitors? This becomes very important because in surgery, doctors use cautery. The frequency of a cautery mixes with the frequency of the leads, causes the artifacts. Okay, so that was one of his wishes. Another anesthetist, Dr. Di Mello, said many times a patient is admitted to a local nursing home or ICU, is on a ventilator, wants to move to a higher institute. Can we have transport ventilators? Okay. There might be some available. They are far-fetched. They are expensive. Can we have indigenous, simpler ones? Okay. She said, as the anesthetist, when the patient comes into the OT, other doctors for various needs have fired all the veins. You cannot even get intravenous access to blood or to give the medication. It is so difficult. So can we have an automated intravenous vein locator? This becomes very difficult or in children, on cancer patients who are on chemotherapy. And her third question was, can we have a patient-controlled analgesia pump? So if I am having chronic pain because of cancer, sitting at home, can I have a pump which can modulate the dose of the drugs, and I can pump myself in a regulated manner? So these are certain questions, just to highlight. They're very simple, but currently we doctors don't have solutions for them. And we need you guys to help us work towards these kinds of things. So while I was going through this wish list and preparing it, last week I got this video on WhatsApp which I'd like to share. And this is something called as a VBot. It's a venous blood collector. This is a US based company which has produced this. I don't know if the video is playing. Yeah, there it goes. So basically what it does, and you can go to the site, I will not go to the whole thing in detail. It uses technology, very simple. There's a robotic arm, and if you see, it will go and the patient puts in the arm, and it will do image analysis, highlight your veins. It will also do ultrasound. It will say if the vein is big enough. It will put in the needle. The person is just collecting the blood sample at the other end. So if you have a pediatric patient, if you have difficult veins, and we face this very often. This is the most common thing done in every hospital and laboratory. Just think about automating it and mass production of this technology. Every lab is going to do it. Okay. Typically, this is a US-based technology. By the time it comes to India, it will be 5 years, 10 years down the line. It will be very expensive. Can we look at indigenization or simpler things? So this is just one example I wanted to share with you of what the various doctors in every field is thinking. Today I am here as a laboratorian, but every doctor will have his or her wish list. So I'm here to present my wish list in a way, or share with you the areas I work in. And two areas I'll touch upon is, one is CBC, which is like a routine test which we do day in and day out. Many of you would have given your blood sample and checked your hemoglobin. That's a CBC test. The other area is blood cancer. That is the main area I work on. And third area, I'll just touch upon a little bit on data analysis from a laboratorian perspective. So I said the most common test, that's the CBC. This CBC machine has been at the forefront of technology change as far as laboratories are concerned. From manual methods, from a hemoglobin measurement which you have to do manually in 1980s, and I have done it with my father in my dad's lab. Okay, so I've done the manual method when I was maybe 8 or 10 years old. And then you had those floor-based machines, then came the bench tops. Now we have almost desktop-sized machines. And my dream would be having a portable machine maybe in your cell phone. And that's the way we are progressing. So this has been at the forefront of technology, and that's why I said, let's start with this machine. Typically, this is a 3-part machine, what we label a simplest machine, which is very popular still in India. This is like a 5-part machine. Typically, from the engineering aspect, it used a simple electrical impedance principle for cell counting. Okay. Now, the newer machines, in addition to electrical impedance, use fluorescent flow cytometry, they use dyes, they use flow cytometry light scatter, they use combination of laser light scatter, radio frequency, conductivity to look at cell populations and differentiate from each other to give us a WBC count. They also look at specific dyes. So you have certain dyes binding to certain cells, which will say, okay, this is this cell and this is some other cell based on a protein or a dye which it binds to. So it's continuously evolving. So if you see, this one gave us numbers and some graphs. This gives the same numbers and graphs. In addition, what it did is automatic analysis of these graphs and gave us some flags and said, okay, in the RBC I have abnormal distribution. There are dimorphic population, 2 sizes of red blood cells. I can see it. There are 2 populations over here, 2 peaks. But an experienced person or a technician who is never trained for doing graphs cannot see it. So the company has automated the interpretation over here and given you, okay, there is dimorphic population. So there is more the software is doing, a better result, a better data for, better use. So what we have done in our lab is, since last year we have on this machine, which is a very small machine, very robust. It's a 5-part, 6-part cell counter. It does a lot of tests. It gives hundreds of research parameters. So people keep labeling them as research parameters because they go to the research labs and never get used clinically. So I like the term advanced clinical parameters, and my passion for the last 4 or 5 years has been to put them into clinical use. How can I put these parameters into clinical use and take them forward? So this is the test which we started. And what all does it do? That in addition to giving you a routine report, which every lab in Mumbai does or India does, I give an additional 1-page report which has a few newer parameters. We have introduced interpretation. We started using these parameters. We made normal reference ranges and started using them. The other thing which we personally do in this machine, and this is just to highlight what more you can do from a single sample, is we do thalassemia screening. If some of you have not heard about thalassemia, a genetic disease, where if a child and if a father and a mother are thalassemia carriers, and a carrier is almost 5% of our population in Mumbai, which is huge, there is 50% chance that a baby will have thalassemia disease. This baby beyond 6 months of life is dependent on blood transfusion and does not live a complete life. So very common disease in our country still, extremely easily preventable. Okay. The thing is, it's very common in Gujaratis, Muslims, Boras, Sindhis, Punjabis, eastern parts of India, because in India we still have caste-based system and caste-based marriages. Okay. So, if somebody asks me, before marriage, kundli padhao, I said no, thalassemia ki screening karao. Okay, because that is far more important for you in your family than to have a kundli read, but you get this test done. And you will see people say, I want to do HIV and hepatitis B. Okay, I want to do hepatitis C for my partner or spouse. But I would say the first thing you should do is get thalassemia screening done. So idea is, why get it done? Can we predict that this patient requires a testing? This is what we have done. Based on thalassemia carriers having small RBC size and high volume, there are numerous formulas available in literature. And around 4 years ago, I published this Sehgal index, and we found it extremely sensitive and specific to our needs. So what we have done is, we have taken use of the technology in this machine, where I can put in my own formulas into the software of the machine. It does the calculation. Patient walks in, my technician runs the sample. Everything is normal. There are no flags, clear. There's something positive sign coming here for my technician. Says read what it is. Goes to the next screen, it says BTT Segal index positive. The technician knows without any calculation this is a thalassemia suspect patient. So when that flag comes to me, I write it in the report, it goes off, the patient gets evaluated for thalassemia, and 85% of them, based on the sensitivity of this, actually turn out to be thalassemia carriers. So we are helping in screening disease. What did I use? I used the MIS or the information system technology available in the machine, the software, put the two together, and I am helping the patient out. This is one example which is currently available and we are doing it. There's another example, malaria, extremely common. Somebody in your family or somebody you know has to have had malaria, especially in the monsoon epidemic. Almost everyone in Mumbai has it. So, how do we detect? You have to go to a doctor, he will say, okay, do a CBC and a malarial parasite test, you have to screen the slide. This particular machine model screens for malaria automatically. So you see there's a flag which comes here which is called as a pre-RBC flag, and here there are some purple dots which are parasitized RBC. This machine has a fluorescent dye, it can bind to the parasites, which based on the light scatter property comes in a particular region. When it is of a certain number, the machine flags it. Currently we do it only for one type of parasite, that is Vivax, which is more common. As we speak, I am currently working with the company on a project for falciparum. So 3 years back we evaluated this flag and we found it to be sensitive 84%, specificity 99%. In practice, what happens? In the monsoon season, when a patient walks into me, they might have walked into me from with a letter from the doctor saying CBC and a urine test. When I ran the CBC, it showed me the flag. I called up the doctor after having seen the slide and confirming it's malaria. And the doctor and the patient are both very happy because he didn't even ask for malaria. And in the monsoon season, 1 out of every 100 patients who walks in with fever, unsuspected, the machine picks it up for us. Okay. Now, rather than me picking it up, my staff comes running to me. I have seen it on the machine. I have confirmed in the slide. I just need to look at it for 10 seconds. And normally I would have wasted around 5 to 10 minutes. Not wasted, but spent that much amount of time. So again, automation, use of technology, something to our local needs. Nowhere in the world, and this company sells its maximum machines in Japan, Japanese-based company Sysmex, and the other end is in US. None of them have malaria. They don't use it over there. Okay. The technology is there. This is in local needs. Okay. So we have been working with them because now it's big business for them. But we need to initiate that technology and take lead of doing this kind of things. Future of CBC, and this is where you guys come in, that what more information can I get from a single sample? That's always my dream. Okay. I run one sample, it should tell me the infection I have, it should tell me whether I'm thalassemic, confirm it for me. Okay, do everything. Can it be portable? Can I pick up other diseases like malaria? Can I pick up dengue? Can I pick up typhoid from the same machine? And we already have non-invasive hemoglobin measurements now. But can we have non-invasive cell measurements? Those are the kind of dreams which a patient would love to have. Walk-ins can get your CBC report. So these are some questions which I just raised. We are potentially looking at what we can do. So next topic I go to is blood cancer diagnostics. How many of you know of flow cytometer or heard of flow cytometry technology? You guys are in the engineering field. So I'm sure you would have, most of you are aware of the flow cytometry technology? The basic principles? Not all of you. So I recommend if you are interested, there's a Thermo Fisher company, very popular company, this is the website, this link is there. This talk will be available for all of you at any time. Go to this link, basics of flow cytometry are given beautifully. There's a huge tutorial, introduction to flow, what it does, what are lasers, what are fluorescent fluorochromes, what are optics. Much easier for you guys to understand than us biologists to understand in that sense. What do we do with flow in our lab? Leukemia, which is blood cancer, we try to diagnose leukemia, we try to subtype it, we try to look at certain markers which will help us say this is a good leukemia, intermediate or a bad leukemia, which will help us in treatment. We look at minimal residual disease, which is looking at 1 in million abnormal cells after a cancer patient has been treated. We pick that cell up and say this patient is going to relapse. The relapse will happen after 3 to 6 months. Can you take some action today? Because we have picked 1 in million cells and give some extra therapy or change the modality of treatment to prevent the relapse of cancer. So these are the kind of things the machine does. And typically we use what we call as CD markers of proteins of different cell lines. So you know WBCs or white blood cells, typically basic biology, T cells, T lymphocytes, B lymphocytes. There are some neutrophils or myeloid series of cells. And every cell has their own markers. Okay. We combine these markers into one panel. So there's one tube which will have T cell markers, one tube which will have B cell markers, the third tube will have myeloid cell markers. Run it through a flow machine. Then we do some data analysis. Okay. These cells, the green ones are CD3 positive, so I know these are T cells. These are 19 positive, so I know these are B cells. This is simply looking at lymphocyte subsets. Then we look at tumor cells and we say, okay, these tumor cells are of B type. These tumor cells are of T type and these are of myeloid type. Because every type has a different treatment, a different prognosis. So this is in just what we do. So instead of going into flow cytometry, I thought for you guys, let's look at from the data analysis perspective, because that might interest you more. Typically, when you're looking at flow cytometry data or any data if you look at, you can see a histogram, very simple. Single parameter, so we are evaluating the intensity of CD45 in the blue cells, which is more than that in pink and orange. Or you can look at a two-parameter plot. You take one protein, CD45, and you look at site scatter, which is nothing but granularity in the cell, and you have comparing two parameters, you can separate populations. When we had one color, two color, three color machines, life was simple. And I remember in 2008, we were using three color machine. There was this advent of a 3D plot. Okay, and I said, wow, instead of looking two antibodies, now I can look at all three together. And this is just 2008, okay, when I just started doing flow cytometry. In the period of time, the flow cytometers have gone from 3 color to what we clinically use now 8 and 10 color. And in research labs, we have 15 and 17 color. The problem is, for a simple 9 color flow cytometer, if you look at different combinations of antibodies, you will have a minimum of 55 unique combinations. This is for one 9 color tube, and we on an average run 3 9 color tubes. Okay, so I have to go back to 165 plots. You can imagine the amount of human error I can make in interpreting these plots. Then look at normals and abnormals, and then I'm talking about detecting 1 in million cells. Okay, so there are a million dots. I have to look for a needle in a haystack. Okay, so this is not going to work. So the field of software analysis is hugely expanding in all fields of science: flow, sequencing, proteomics. And one of the softwares, Infinisight for example, is using principal component analysis. I'll not go into the details. And there's a very beautiful paper related to flow which says end of gating. And if you say upper line shows you 1965 onwards, the hardware progress. Beyond 2000, path breaking progress has been less. Software progress is all 2000 onwards. And every 2 years you have something new path breaking coming up. And these are some softwares which are used in different modalities. Instead of looking dot plots, there is something called a SPADE. This is, even the names are confusing. It's called as stochastic neighbor embedding. Okay, the names are too complex for doctors like us. I had to really mug this up to even, share it with you. So there are heat maps, there are phenographs, there are different kinds of software available which are doing it. We doctors don't understand anything about it. We need help from data scientists to come and guide us to how to use it, to make indigenous softwares to our needs again. And that is where, people like you guys can come in as data scientists for healthcare. Future of cytometry, and I think my personal interest or interacting with the proteomics lab for so long, I get to learn a lot. I get to learn about fields which I have never been exposed to. In the few projects which I have shared, I learned a little bit about mass spectrometry and Maldiv. I never knew a word about it. And by the time in the last 5 years I see the field of flow expanding, what is it doing? The latest instrument coming to the market or in the future will be combination of mass spectrometry and flow cytometry. It's called as mass cytometry because the limitation of flow cytometry is this: every fluorochrome I use has an excitation wavelength. It overlaps with the next fluorochrome, it overlaps with the next fluorochrome. So separating or the resolution is not that good. I can use a maximum of 5, 6, 8 or 10. Now instead of labeling my cell proteins with fluorochromes, I am going to label it with heavy metal ions. So I can use 100 or 200 and separate them out. Very simply put, and I don't know too much about it. If you have any questions, Dr. Sanjeeva is the right guy to ask about mass spec. The idea is, once this comes into practice from a clinical, I'll stay in the cell surface or I'll stay in the cell cytoplasm, put it through mass spec, it will give me the data. What interests me even more, the data, final data generated, as I said, I am more interested in the data. The output is exactly similar, the same file called as FCS 3.0 file, okay, which is called as the flow cytometry standard file. I can analyze it the same way I have been analyzing flow cytometry data. Okay. So I have already used to analyzing the data. This is for my clinical needs. The technology used is different, and I get far more data. The software used will be different. So that's what excites me. So one example which I showed you in that T versus B plot, there were around 6 antibodies in that tube. Okay. This is the simplest of site of data. It has 27 antibodies, simply doing only lymphocyte subsets, only cell surface antigens. Fascinating, for me at least, because it's the way the technology is moving. So this is just to highlight that how fast things are moving, and bioinformaticians, data scientists is going to be the key one. And hence I wanted to put in laboratory data analytics. It's a nice article by Dr. Harvey. He's from Quest Diagnostics USA, and he says historically we laboratory people have been, just transcriptional enterprise or translational enterprise. Somebody gives a sample, we collect it, we run the test, we report it, full stop. We need to look beyond this traditional approach. We need to go and say, let's go back to my data and analyze what more can I get out of it. Okay? And actually, if you read a very good article from Harvard Business Review, it says data scientist as the sexiest job of the 21st century. Okay, and I completely agree to him. If I was given an opportunity, I would go back and start looking at data from my own lab. Okay, so we generate billions of test results in our country every single day. You can, if you guys know, every new startup is behind collecting data. Okay, and I have been approached at least by 6 or 7 startups who are coming to me. Can you share your patient data? Currently, there are huge medico-ethical problems because in India we don't work with consent, with paperwork. We do not work, so we don't know how somebody is going to use. So it's a problem. Okay. But most of the medical startups I am seeing in the pathology sector are all after data. I'll tell you the reason why. Okay. So when I first heard the term big data, it was in connection to next-gen sequencing. And simply for me, as I said, with most laboratorians, big data means big in size. That's all I knew about it. I still don't know much about it. Am I worried about there? I'm not even worried about what next-gen sequencing will do. I am not doing it in practice, but it's coming in a big way. What I'm worried is, what about the vast or the really big amount of data sitting in my own laboratory information system? And it's a mine, it's about somebody sitting there and mining it. And I know one doctor, Dr. Swayam Prabha, they have an Anand pathology lab in Bangalore. It's a 5-storied lab. They actually currently have hired, it's a clinical pathology lab. They have hired 2 data scientists, both full-time, only looking at data for the last few years from their own laboratory. It's fantastic. And the examples which he showed, and one of the examples I'll show to you, this is from what he shared with us. Okay, and this is where I feel, or he feels, we should be having seamless data connection. Forget about the technology part which I showed you. Okay, imagine this 60-year-old gentleman who walks into a hospital. He gives one CBC sample which goes to the hematology lab, and they say he has iron deficiency anemia. The report is gone from their lab. My job is over. He now goes, gives a sample. The sample goes to a stool sample which goes to a clinical pathology lab. The lab is separate. Technician is separate. Doctor signing the report is separate. He says small amount of blood in stool. He gives out the report. He goes to the radiology department. He says, I suspect small abdominal mass close to the intestines. He gives out the report. Now the patient collects the report. In a good hospital, the report goes to the doctor. If you have a very good expert, he will go through all the 3 reports, collate the data, assemble in his mind and say, are the 3 related? Okay. But if my laboratory information system data gives me thousands of patients who are exactly the same, in majority of them, there was actually a mass in their intestine, which was actually a cancer, which was the cause through all the 3 reports, collate the data, assemble in his mind and say, are the 3 related? Okay. But if my laboratory information system data gives me thousands of patients who are exactly the same, in majority of them, there was actually a mass in their intestine, which was actually a cancer, which was the cause of all 3, the probability of the algorithm working is far higher. And my dream, or what Dr. Anand presented was, basically, and this is extremely common, that in practice, if you tell me a 65-year-old gentleman has iron deficiency anemia, the first thing I'll say, if he's well off and not having nutritional issues from a well-to-do family, let's get you screened for stool occult blood and a ultrasound. Because colonic cancers are known to cause this. Okay? This data is there in the system. It's only for somebody to build this algorithm and give it to the laboratory. Something similar to what I showed you about thalassemia screening. Data is all there. We put an algorithm, the staff picks it up. We put the algorithm in the HIS or the hospital system, it will flash. If it flashes, doctor will not even miss it even if he is not an expert. So that is what sort of seamless data analytics or data scientist can do. So this is the three things I wanted to share with you, and I think I've taken enough time. Thank you for patient hearing, and love to have questions from you, from your perspective. Thank you so much. His question is, if you collected the data of every patient over the last, say, 10 years, can you pick up the new patient a little earlier based on the data analysis? This is what an expert physician does. Okay. So, but the problem is, when I have fever, the first person I will approach is my parents or a family physician or a local doctor. He will give you some medication. If it doesn't resolve, he'll say, okay, go to an MD physician. And he'll do a couple of tests. Okay. If it doesn't resolve, he'll send you to another expert. And okay, he will see 2-3 more tests and he'll send you to another expert. So by the time you reach the expert and you've gone to 10 or 12 tests. Okay. So now why does the hematologist pick up that these are signs of blood cancer? Because fever can be due to anything. Because he's not looked only at fever. He has looked at fever, he's looked at my CBC report where I had low platelets, where I had some query abnormal cells. I have certain enzymes which in my body are high. Okay. I have a slightly enlarged liver on ultrasound. And doctor knows A plus B plus C plus D is potentially a sign of blood cancer. So if this patient had directly gone to the hematologist right up front, he could have picked it up. But that also means every person who has fever should go directly to the hematologist. That is not possible. And in our country, it's never going to happen. Okay. That's where exactly what you said. For example, we ran around 400 cases of leukemias or blood cancer last year in our lab. Related, not all blood cancers, lymphomas, leukemias, other types of samples. Currently, what I'm going to sit and manually do is cipher through the data, try and understand which marker came in which diseases, which was a rare disease, which is the common problem. Okay, is this disease rare, is this disease common? In a small private laboratory, it becomes very difficult. Even in an institute like Tata Memorial Hospital, they go to 30 cases a day. It's almost like doing 1,000 cases a month. Okay, and they do almost 5,000 cases of new cancer patients of blood cancer every year. Okay, imagine if there's a software which automatically collects from the reports every data, and a data scientist is there. He may not know the biological interpretation, but he'll say, okay, this looks something different to me. Okay, this looks something different to me. Does it make clinical sense? So we need to talk. Okay. So that's exactly what a clinician does, but that's where data algorithms can really help. Some patients come with my red color urine. Do I have blood in urine? And you go back and ask them, did you start on vitamin B12 or iron tablets? That causes red color urine. Okay, very common. Okay. You have red color urine, there are thousands of causes, but what we read on Google is cancer first. We read TB first. So that's dangerous. But not going to self-analysis, I'm looking at data analytics from a point of view of the reports, the system, not looking at the technology, but community data, disease trends. Monsoon season and malaria, everyone knows. But I don't know about a cancer patient coming to Tata Hospital from a certain region of Bengal. Is there something else environmentally happening there? Okay, can we look into it from a preventive angle? So that's what data can give you. Okay, thank you very much.